Welcome! Today we're learning that complex numbers are very well suited to solve geometrical problems in the real plane. We're going to take a look at how the absolute value can be applied to geometry. We won't be needing the complex conjugation, but remember, these two are intimately connected. We start with this equation, which has two absolute values, left and right. We want to find all complex numbers that satisfy this equation. The absolute value of z plus 1 has to be the same as the absolute value of z minus 1 minus 2i. We're going to solve this equation in two ways. First, the algebraic way, and then much cleverer and better adapted to this problem, the geometric way. But let's start with the algebraic solution. For this we write z as x plus yi, as always very important that x and y be real numbers. And then we simply plug in and have a look at how the left and right sides turn out. Okay, on the left hand side we have z plus 1, which is x plus yi plus 1. To add these numbers, I add the real parts, so x plus 1, and the imaginary part stays y. So now by definition of the absolute value, this is nothing but the square root of the sums of squares of the real and imaginary part. So we end up with this expression here. Very important, not yi squared, which would give you a minus sign here, but the imaginary part is simply y. So this is the left-hand side, and in the same way we write the right-hand side. So we plug in this, then we take the real parts, which gives us x minus 1, then the imaginary parts, which gives us y minus 2i, and then again we apply the definition of the absolute value. So now we plug in these two square roots in this equation and try to solve for y of x. Okay, let's do it. Of course, the first step is to get rid of the square root. In general, you have to be very careful when squaring an equation, because this is in general not an equivalence. But here, because both sides cannot be negative, squaring gives you an equivalent equation. Very, very important. Please make a little note that here we have an equivalence. Okay, then we apply the binomial formulas and see what we end up with. Okay, this is good. Y squared cancels, as well as x squared. So we have a linear relation between y and x, and we're going to solve for y. Okay, I take 4y to the left-hand side, then this 1 here also cancels. I forgot to say that before. Then I take 2x here, which gives me minus 4x plus 4. And after dividing by 4, I end up with y equals minus x plus 1. So the solution set of this equation here consists of all the complex numbers x plus yi, where y is minus x plus 1. And this, of course, is nothing but a line in the real plane. So the slope of this line is minus 1, and it meets the y-axis or the imaginary axis at 1. So the set of solutions geometrically represented is this line in the complex numbers, which, remember, are nothing but real vectors with two entries. Okay, nice. So we found the solutions of this equation, but this here is just dumb calculation without any insight. And we have no idea what the slope of this line and here this point has to do with these two numbers. So as I said before, the geometric solution is a much better way to solve this equation. We're going to take a look at that now. Before we do that, a very important observation. If this is the origin of the Gaussian plane, the complex plane, then I can identify points in the real plane with the coordinates x, y with complex numbers x plus yi. So I identify a point with this vector, meaning complex number that is pointing to this point. In the same way, here is the point w, and associated with it comes the complex number w. Now this yellow arrow is nothing but z minus w, because minus w points from here to here, plus z, and I end up here. Or another way to look at that, if I add w and this vector, I end up here. So w plus this vector is z, or this vector is z minus w. So here z minus w is the vector pointing from capital W to capital Z, which means that the length of this vector, which is nothing but the absolute value of this complex number, is the distance from W to Z. Okay? Now, I rewrite this slightly. Z plus 1 absolute value is Z minus minus 1 absolute value. Now we have a complex number here, which I call small w1, which lies here. So this is the point w1, and this is the complex number associated with it. And this is nothing but the distance from the point Z to this point here. The same way, the right-hand side can be rewritten like so. And this is nothing but the distance from the point capital Z to this point, 1, 2. Yeah, associated to this complex number, 1 plus 2i, the point 1, 2, which is here. And with this geometric interpretation, it's very easy to solve this equation, because what we're looking for are all the points in the two-dimensional plane, which, remember, correspond one to these complex numbers, that have the property that they have the same distance to these 2 points. An obvious solution would be here in the middle of these points. So this here is just the middle, M, W1, W2. But there are a lot more points that satisfy that they have the same distance to these points. They all lie on a perpendicular line to the connection of W1 and W2 passing through this middle point. Okay, I erased this vector here because we don't really need it. This is a much better solution to this problem, because here we see the geometric meaning of these two numbers, 1 and minus or 1 plus 2i. They correspond to these points, and the line perpendicular to this connecting line here through the middle contains or consists of all the solutions. These are all the solutions. In German there's a nice word for this line, it's the Mittelsenkrechte of these 2 points. In English, I don't know if there's such a catchy term. All I could find was perpendicular line to this line here going through the middle. If there's a better term, please write it in the comments. Okay, I hope you have been able to see that this solution is superior to the previous one in the sense that it really contains the geometry of this problem. But of course it's not forbidden to use the algebraic method if you can't think of the geometric solution. Next example, we are looking for all the complex numbers that satisfy this equation here. The absolute value of z minus 1 plus 2i is 2. First, again, the algebraic solution. As before, we write z as x plus yi with real and imaginary part x and y, and we plug that in here. As before, we're pairing up real parts, x minus 1, imaginary parts, y minus 2. Here, because of this minus, we have y minus 2. And we end up with, as before, this square root of x minus 1 squared plus y minus 2 squared has to be 2. Now, if you've never seen an expression like this before, it's kind of hard to realize what numbers x and y satisfy it. If you have seen it before, it should be clear to you that this represents a circle with radius 2, and the center of this circle is simply this number 1 plus 2i, or written as a real tuple y1, 2. Okay, drawing circles on this blackboard using this is not my favorite thing to do, and this is not really a circle, but you get the idea. Now to explain this here, I pick any point on the circle, xy, and then if I take the length of this here, this is x minus 1, absolute value because x could be negative, and here we have y minus 2, absolute value, because in this case this is negative, but the absolute value is not so important because using the Pythagorean theorem, here I have a rectangular triangle. By Pythagorean's theorem, this is exactly what you have here. So this length here is 2, and then this square root. This guy here squared plus this guy squared, square root of it is the length of this yellow arrow, and this is 2. And then it is obvious that this represents a circle with center 1, 2 and radius 2. Okay, and again, the geometric solution is way better than the algebraic solution. But of course here, this is not so bad because it's not as long as this calculation, but maybe you don't recognize the circle from here. Now, in the geometric solution, we are looking for all the points xy, again corresponding to the complex numbers that satisfy this equation, which have distance 2 to this point, because here, by this observation, this is nothing but the distance from w, which is this point, 1, 2, corresponding to this complex number, 1 plus 2i, to our points z. And then, of course, this is obvious. If I'm looking for all the points that have a given distance to one point, they lie or they form, they build, I don't know. They are the circle with a center w and radius 2. Done. Okay? So here I'm looking for all the blue arrows that have the property that the length of this yellow arrow pointing from w to here, this endpoint, has length 2. And then, of course, all the points on this circle satisfy this equation and the other way around. Okay, this has been a little application of the absolute value to geometrical problems. Of course, this was just a glimpse. If, for example, you're interested in doing Olympiad problems, then complex numbers can be very, very useful to reduce awfully complicated problems to simple calculations. Well, not so simple, but easier calculations using conjugation, absolute value, and some algebraic tricks. Okay, I hope that was enjoyable. Thanks for watching, and I'll see you soon.